Okay, welcome to today's session, guys. So the question that we're looking at today reads: find the differential coefficient over y of x using logarithmic differentiation. So the function that we've been given here is y of x is equal to the square root of 1 plus cos squared x divided by the square root of 1 plus sin squared x there. So now, the first thing that we have to do is we need to convert these roots that we have there and write them in terms of powers. So when we do that, we're going to have y of x is equal to 1 plus cos squared x to the power half there, divided by 1 plus sin squared x to the power half there. Then after we do that, we're going to introduce logs on both sides of the equation that we have there. So I've lean y this side and also I've lean this part here. So now, according to the properties of logs there, if you are dividing the things that are inside there, this here becomes ln y is equal to ln the numerator cos squared x to the power half minus ln open brackets 1 plus sin squared x to the power half there. So now we can utilize another property for logs there. If you got a power like this, it can be dropped this side. So we're going to have ln y there. Okay, so ln y is equal to half ln open brackets 1 plus cos squared x minus, also drop that half there. We have 1 over 2 ln open brackets 1 plus sin squared x, like this. So now, after we've done this, we're going to say differentiating throughout with respect to x. So when you differentiate throughout with respect to x, we're just going to write the notation showing that we're differentiating with respect to x. This function this side, we differentiate it with respect to x, equal to, we differentiate this term there with respect to x, cos squared x, we also differentiate that term there with respect to x. One plus sine squared x, like this. So now we're going to start differentiating this side. Of course, we know to say if you differentiate y with respect to x, we're going to differentiate y the normal way and multiply the derivative of y with dy dx there. So that method of differentiation is called the implicit differentiation. So this part is going to be 1 divided by y dy dx equal to, if you differentiate this part here, we're first going to differentiate this whole function the way it is there. We're going to have 1 over 2 multiplied by, if you differentiate this, we're going to get 1 plus cos squared x there. Then we differentiate what's inside there, we're going to get negative 2 sin x cos x minus this side here, what they have there. So we're going to have half multiplied by, if you differentiate this function first the way it is there, you're going to get 1 over 1 plus sin squared x there. Then if you differentiate 1 plus sin squared x there, we're going to get 2 sin x cos x, like this. So then we continue this side, we're just going to write it the way it is here. 1 over y dy dx is equal to, then this part we have negative 2 sin x cos x divided by, we can multiply the numerator or the denominator rather with 2 there. We have 2 plus 2 cos squared x minus 2 sin x cos x divided by 2 plus 2 sin squared x like this. So now, since we know to say 2 sine x cos x is equals to sine 2x there, so this is a trigonometric identity that we have there. So meaning that where there's 2 sine x cos x, we're going to put sine 2x there. So then we have 1 over y dy dx equal to negative sine 2x divided by 2 plus 2 cos squared x minus, even this part here where there's a sine 2 sine x cos x, we put sine 2x there, sine 2x divided by 2 plus 2 sine squared x like this. So now here, since the whole purpose of this question here, we're taught to find dy dx at this side, so we're going to multiply it throughout by y. So if we do that, we're going to have dy dx this side is equal to y multiplied by negative sine 2x divided by 2 plus 2 cos squared x minus sine 2x divided by 2 plus 2 sine squared x like this. So then the final step now, where there's y, we're just going to make a replacement by putting the original equation, the original function that we have there. So then our dy dx then is equal to, so the function of y is the root of 1 plus cos squared x like this, divided by the root of 1 plus sine squared x, open brackets, negative sine 2x divided by 2 plus 2 cos squared x minus sine 2x there divided by 2 plus 2 sine squared x there. So this here is the solution to this function of x that we are given there. Okay, so let's look at the next question there. Okay, so the next question that we have there, y of x is equals to x plus 3 divided by the cube root over x squared minus 4 there. So the method of differentiation that we're going to use here is logarithmic differentiation. So what we're going to do here is this cube root that we have there, we're going to write in terms of a power first. So this here is the same as y of x there is equal to, so this here is the same as y of x is equal to x plus 3 divided by, open brackets, x squared minus 4 to the power 1 over 3 there. So we've written it in terms of our powers there. So now what we're going to do next, the next step that we're going to do there is we're going to introduce logs on both sides. So we're going to say ln y is equals to ln, open brackets, this side, the whole of this function, x plus 3 divided by x squared minus 4 to the power 1 over 3 like this. So now, after doing this now, we're going to utilize the properties of our logs. So if you are dividing, this is the same as ln y is equals to ln, open brackets, the numerator there, x plus 3 minus ln, open brackets, x squared minus 4 to the power 1 over 3 there. So then you can still utilize the properties of logs there by dropping this power this side. So we have ln y is equal to ln, open brackets, x plus 3 minus, when we drop the power, we're going to have 1 over 3 ln, open brackets, x squared minus 4 like this. So now, if that is the case there, then now here we're going to differentiate throughout with respect to x. So I say differentiating throughout with respect to x. So if we do that, we're just going to show that now we're differentiating with respect to x. Differentiating this function with respect to x, we have ln y this side equal to, we differentiate this function with respect to x, in open brackets x plus 3 there, minus, we differentiate with respect to x as well, that function there, 1 over 3 in open brackets x squared minus 4, like this. So now once we do that, here differentiating this here, we're going to differentiate y with respect to x. So what we do here is we differentiate this the normal way, like we're differentiating with respect to y there, and we multiply the derivative that we're going to find there with dy dx. So when you differentiate this, you're going to get 1 over y, and you multiply it with dy dx, like this. So this method of our differentiation there is called implicit differentiation. So we continue differentiating what is on the right hand side there. So if we differentiate this there, we're just going to get 1 over x plus 3 minus, we're going to keep first the coefficient that we have there, 1 over 3 multiplied by, when you differentiate this, you're going to, the first things first, you differentiate ln x squared minus 4, you're just going to get x squared minus 4 there. If you differentiate what's inside there, you're going to get 2x, like this. So then, after doing that, we're just going to multiply throughout with y, because we just want to remain with dy dx this side. So when we do that, we're going to have dy dx is equal to y multiplied by 1 divided by x plus 3 minus 2x. If you multiply 3 by x squared, we're going to have 3x squared. 3 by 4, we're going to get negative 12 there. Okay, so now what we're going to do there is, while there's y, we're just going to make a substitution, or rather a replacement with the original function there. So then we have dy dx is equal to the function of y, what, x plus 3 divided by the cube root of x squared minus 4, like this, open brackets, 1 over x plus 3 minus 2x divided by 3x squared minus 12, like this. So this here is the solution, or rather is the derivative of y with respect to x of this function that we have there. Okay, so thank you, see you in the next video.